Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the General Chemistry Review, Chapter 12, Electrochemistry. Oh, I should change the title on this, huh? Electrochemistry. All right. The mitochondria are powerhouses of energy. The prime purpose of the mitochondrion, is to manufacture a deliverable and usable form of energy. By now you are well aware of the complex processes by which the potential energy in the chemical bonds of carbohydrates, amino acids, and lipids is converted into the potential energy of the phosphate bond in adenosine triphosphate, ATP. ATP is then delivered to different parts of the cell where it is used to energize most of the processes essential to the maintenance of life. The mitochondria generate tremendous amounts of ATP in humans. The average daily turnover of ATP is more than 50 kilograms. Without a continuous supply and replenishment of ATP, we wouldn't survive. ATP powers the contraction of our heart muscle and maintains the membrane potential essential for neurological function, among thousands of other essential roles. How do the mitochondria manufacture these packets of life-sustaining energy? Remember that mitochondria rely on their double membrane structure to carry out the electron transport chain and oxidative phosphorylation. As such, mitochondria truly act as batteries of the cell. In fact, note the similarity between the proton motive force of the mitochondria and the electromotive force of electrochemistry. Are these two terms the same thing, or at the very least similar in nature? Indeed, mitochondria and batteries do function in similar ways. Specifically, mitochondria function most similarly to a concentration cell. In both concentration cells and mitochondria, a concentration gradient of ions between two separated compartments connected to each other by some means of charge conduction establishes an electrical potential difference or voltage. This voltage, called electromotive force in a concentration cell and proton motive force in the mitochondria, provides the drive to move charge from one compartment to the other, creating current. In the concentration cell, an oxidation-reduction reaction takes place, and electrons move in the direction that causes the concentration gradient to be dissipated. In the mitochondria, the charge buildup is in the form of a hydrogen ion, or proton gradient, between the intermembrane space and the matrix. Embedded in the inner membrane is ATP synthase, which serves a dual role as a proton channel and a catalyst for the formation of the high-energy phosphate bond in ATP. As the hydrogen ions flow down their electrochemical gradient, energy is dissipated, and this energy is harnessed by ATP synthase to form ATP. In this final chapter of the General Chemistry Review, we will focus our attention on the study of various electrochemical cells, utilizing our knowledge of oxidation-reduction reactions from Chapter 11. We will study how these principles can be applied to create different types of electrochemical cells, including galvanic or voltaic, electrolytic, and concentration cells. Regarding the thermodynamics of electrochemistry, we will focus on the significance of reduction potentials and examine the relationship between electromotive force, the equilibrium constant, and Gibbs free energy. Electrochemical cells. Electrochemical. Electrochemical cells are contained systems in which oxidation-reduction reactions occur. There are three fundamental types of electrochemical cells: galvanic cells, also known as voltaic, electrolytic cells, and concentration cells. In addition, there are specific commercial cells such as nickel-cadmium batteries through which we can understand these fundamental models. Galvanic cells and concentration cells house spontaneous reactions, whereas electrolytic cells contain non-spontaneous reactions. Remember that spontaneity is indicated by the change in Gibbs free energy, delta G. All three types contain electrodes where oxidation and reduction take place. For all electrochemical cells, the electrode where oxidation occurs is called the anode, and the electrode where reduction occurs is called the cathode. Let's write that down. Let's write that galvanic cells are spontaneous. Electrolytic cells non-spontaneous. And oxidation occurs at the anode. And reduction at the cathode. Other descriptors of electrochemical cells include the electromotive force, which corresponds to the voltage or electrical potential difference of the cell. If the EMF is positive, the cell is able to release energy. Delta G is less than 0, which means it is spontaneous. If the EMF is negative, the cell must absorb energy. Delta G is greater than 0, which means it is non-spontaneous. So positive EMF for the galvanic and negative EMF for the electrolytic. Furthermore, we could also state that for all electrochemical cells, the movement of electrons is from anode to cathode, and the current runs from cathode to anode. This point can be a point of confusion among students in physics. It is typical to state that current is the direction of flow of a positive charge through a circuit. This model was first proposed by Ben Franklin and continues to be used among physicists today. Modern chemists are interested in the flow of electrons, but may discuss the current, a theoretical flow of positive charge, as a proxy for the flow of electrons. The current and the flow of electrons are always of equal magnitude, but in opposite directions. So, current goes that way, while electrons actually go that way, from anode to cathode. Last, it is important to note that all batteries are influenced by temperature changes. For instance, lead-acid batteries in cars, like most galvanic cells, tend to fail most in cold weather. The thermodynamic reasons behind this will be discussed later in this chapter. Galvanic or voltaic cells. All of the non-chargeable batteries you own are galvanic cells, also called voltaic cells. Accordingly, because household batteries are used to supply energy to a flashlight or remote control, the reactions in these cells must be spontaneous. This means that the reaction's free energy is decreasing. Delta G is less than 0 as the cell releases energy to the environment. By extension, if the free energy change is negative for these cells, their electromotive force must be positive. The free energy change and electromotive force always have opposite signs. Let's examine the inner workings of a galvanic cell. two electrodes of distinct chemical identities are placed in separate compartments, which are called half cells. The two electrodes are connected to each other by a conductive material such as a copper wire. Along the wire there may be various components of a circuit such as resistors or capacitors, but for now we'll focus on the battery itself. Surrounding each of the electrodes is an aqueous electrolyte solution composed of cations and anions. As shown in the Daniell cell illustrated in figure 12.1, the cations in the two half-cell solutions can be of the same element as the respective metal electrode. Connecting the two solutions is a structure called a salt bridge, which consists of an inert salt. When the electrodes are connected to each other by a conductive material, charge will begin to flow as a result of an oxidation-reduction reaction that is taking place between the two half cells. The redox reaction in a galvanic cell is spontaneous, and therefore the change in Gibbs free energy for the reaction is negative. As the spontaneous reaction proceeds towards equilibrium, the movement of electrons results in a conversion of electrical potential energy into kinetic energy. By separating the reduction and oxidation half reactions into two compartments, we are able to harness this energy and use it to do work by connecting various electrical devices into the circuit between the two electrodes. All right, and in this diagram, 12.1, you have zinc and SO4 in the anode side. You have copper and SO4 in the cathode side, and the cathode is made out of copper, and likewise the anode is made out of zinc. I wanted to write down, no, I'm going to make a little diagram. That's what we're going to do. So we got anode, cathode, salt bridge. We got Cu2 plus, SO4 2 minus, and copper right there. We got some zinc on the left side, along with zinc 2 plus ions and SO4 2 minus. In the Daniell cell, a zinc electrode is placed in an aqueous zinc. SO4 is called sulfate, zinc sulfate solution. And a copper electrode is placed in an aqueous copper sulfate solution. The anode of this cell is a zinc bar, where zinc is oxidized to zinc 2 plus ions. The cathode is the copper bar, and it is the site of the reduction of copper 2 plus ions to solid copper. The half-cell reactions are written as zinc to zinc 2 plus ions and 2 electrons, and then the copper side, copper 2 plus ions plus 2 electrons makes copper, solid copper. And each of the half reactions has an electrical energy associated with it. The first one is minus 0.7, the second one is plus 0.3, The net reaction is zinc plus copper 2 ions makes zinc 2 ions plus copper with a potential energy of 1.1 volts, I guess, for a mole of it. So let's write down oxidation and reduction. So there's oxidation on the left and reduction on the right. Oxidation is zinc to zinc ions. Reduction is copper ions to solid copper. We will discuss the calculation of cell potential in the next section. For now, appreciate that the calculation can be accomplished by knowing each half reaction. If the two half cells were not separated, the copper 2 plus ions would react directly with the zinc bar and no useful electrical work would be done. Because the solutions and electrodes are physically separated, they must be connected by a conductive material to complete the circuit. However, if only a wire were provided for this electron flow, the reaction would soon stop because an excess positive charge would build up on the anode and an excessive negative charge would build up on the cathode. Eventually, the excessive charge accumulation would provide a counter voltage large enough to prevent the oxidation-reduction reaction from taking place, and the current would cease. This charge gradient is dissipated by the presence of a salt bridge, which permits the change of cations and anions. The salt bridge contains an inert electrolyte, usually potassium chloride or NH4NO3 ammonium nitrate, which contains ions that will not react with the electrodes or with the ions in solution. While the anions from the salt bridge, like the chlorine, diffuse into the solution on the anode side, the zinc side, to balance out the charge of the newly created zinc ions, the cations of the salt bridge, the potassium, flow into the solution on the cathode side, the copper side, to balance out the charge of the sulfate ions left in solution when the copper ions are reduced to solid copper and precipitate onto the electrode. This precipitation process onto the cathode itself can be called plating or galvanization. I want to write some of that down. That salt bridge electrolyte might be KCl or NH4NO3. And the anode dissolves on the anode side to make up for the increase in charge. And the potassium, the cathode side, will flow over across the salt bridge to the copper side to make up for the decrease in charge. So KCl, Cl will go to the left and K will go to the right. But you can't see that when I draw it like that. I wish I drew my thing different, but it's all good. Cathode and anode. galvanization, plating. During the course of the reaction, electrons flow. Did we already read that? No. During the course of the reaction, electrons flow from the zinc anode through the wire and the copper cathode. A voltmeter can be connected to measure this electromotive force. As mentioned earlier, the anions, the chlorine, flow externally from the salt bridge into the zinc sulfate, and the cations, the potassium, flow externally from the salt bridge into the copper sulfate. This flow depletes the salt bridge, and along with the finite quantity of copper in the solution accounts for the relatively short lifespan of the cell. A cell diagram is a shorthand notation representing the reactions in an electrochemical cell. The cell diagram for the Daniell cell is as follows. Zinc in solid form, and there's a bar, zinc 2 plus, 1 molar, and then copper 2 plus, 1 molar, and copper in solid form. The following rules are used in constructing a cell diagram. The reactants and products are always listed from left to right in this form. Anode, anode solution, cathode solution, cathode. A single vertical line indicates a phase boundary. A double vertical line indicates the presence of a salt bridge or some other type of barrier. Electrolytic cells. When comparing and contrasting galvanic and electrolytic cells, it is important to keep straight what remains consistent between the two types of cells and what differs. All types of electrochemical cells have a reduction reaction occurring at the cathode, an oxidation reaction occurring at the anode, a current flowing from cathode to anode, and electron flow from anode to cathode. However, electrolytic cells, in almost all of their characteristics and behavior, are otherwise the opposite of galvanic cells, whereas galvanic cells house spontaneous oxidation reduction reactions that generate electrical energy. Electrolytic cells house non-spontaneous reactions that require the input of energy to proceed. Therefore, the change in free energy for an electrolytic cell is positive. This type of oxidation reduction reaction driven by an external voltage source is called electrolysis, in which chemical compounds are decomposed. For example, electrolytic cells can be used to drive the non-spontaneous decomposition of water into oxygen and hydrogen gas. Another example, the electrolysis of molten salt is illustrated in figure 12.2. And we have something similar to the galvanic cell, but kind of opposite. Let's draw this as well. You have a bath of salt, water, you have an electrode, you have a chlorine on the left, you have salt or sodium on the right. You have a plus, you have a minus. Why is the plus on the anode? and the minus is on the cathode. Well, either way, you have a loop connecting the two electrodes, and you have electrons flowing clockwise. I guess you have to have a battery too, huh? So let's put a little battery there, the positive end in the counterclockwise direction, the negative end in the clockwise direction. All right, in this electrolytic cell, molten sodium chloride is decomposed into chlorine 2 gas and sodium, solid or liquid sodium. The external voltage source, a battery, supplies energy sufficient to drive the oxidation reduction reaction in the direction that is thermodynamically unfavorable or non-spontaneous. In this example, sodium plus ions migrate toward the cathode, where they are reduced to Na, to sodium, liquid sodium. At the same time, chlorine ions migrate toward the anode, where they are oxidized to chlorine 2 gas. Notice that the half reactions do not need to be separated into different compartments. This is because the desired reaction is non-spontaneous. Note that sodium is a liquid at the temperature of molten sodium chloride. It is also less dense than the molten salt, and thus it is easily removed as it floats to the top of the reaction vessel. This cell is used in industry as the major means of sodium and chlorine production. You may wonder why one would do so much work to obtain more pure sodium and chlorine. Remember that these elements are never found naturally in their elemental form because they are so reactive. Thus, to use elemental sodium or chlorine gas in a reaction, it must be manufactured through processes such as these. Michael Faraday was the first to define certain quantitative principles governing the behavior of electrolytic cells. He theorized that the amount of chemical change induced in an electrolytic cell is directly proportional to the number of moles of electrons that are exchanged during the oxidation-reduction reaction. The number of moles exchanged can be determined from the balanced half reaction. In general, for a reaction that involves the transfer of n electrons per atom, m to the n plus n times e, the electrons, goes to m in solid form, m of s. According to this equation, 1 mole of metal, m parentheses s, will logically be produced if n moles of electrons are supplied to 1 mole of m ions. Additionally, the number of moles of electrons needed to produce a certain amount of m can now be related to the measurable electrical property of charge. 1 electron carries a charge of 1.6 times 10 to the minus 19 coulombs. The charge carried by 1 mole of electrons can be calculated by multiplying this number by Avogadro's number as follows: 1.6 times 10 to the 19 times 6.02 times 10 to the 23 equals 96,485 coulombs per mole of electrons. This number is called the Faraday Constant, and 1 Faraday is equivalent to the amount of charge contained in 1 mole of electrons. 1 Faraday equals 96,485 coulombs, or 1 equivalent. On the MCAT, you should round up this number to 10 to the 5, 10 to the 5th power, to make calculations more manageable. Should we write this down? Let's write a couple of these down. We have m N plus Ne to the minus goes to M in solid form. M to the N, I guess, is N electrons per M. N electrons per atom M. N moles of electrons let's also do the Faraday constant F. 1F equals 96,485 coulombs, which is around 10 to the 5th. The electrode deposition equation summarizes this process and helps determine the number of moles of element being deposited on a plate. Moles of M equals IT over NF, where the mole M is the amount of metal ion being deposited at a specific electrode, I is current, T is time, N is the number of electron equivalents for a specific metal ion, and F is the Faraday constant. This equation can also be used to determine the amount of gas liberated during electrolysis. Let's write down the electrodeposition equation. Electrodeposition. Moles of M, IT over NF, where we have current, time, constant, and moles of electron equivalents. An example: what mass of copper will be deposited on a Daniell cell if a current of 2 amps flows through the cell for 3 hours? Well, what mass? We're looking for moles of M. We know 2 amps times 3 hours. Did they say time was in hours? They didn't say hours. Down here, they're using seconds per hour, so they're converting into seconds. So how many seconds in an hour? 60 minutes times 60 for seconds is 3,600. So maybe that times 3 for 3 hours is 10,800. 10,800 seconds. Mole equivalents of electrons. They say a Daniell cell uses copper electrodes. copper sulfate, because the oxidation state of copper in solution is +2, N equals 2. So N is 2, and then our Faraday constant, which we're going to estimate, they use the full number. But I'm still going to put the rest in my calculator just for ease. Times 2 divided by 2 divided by 10,000. 1, 2, 3, 4, 10. 1, 2, 3, 4. 10 to the 5th. Is it 10 to the 5th or is it 10 to the 4th? No, it's 10 to the 5th. 2, 3, 4, 5. .1 moles. Actually 0.11. I got 0.108. 0.11. I would round that to 1.11. And we must determine the actual mass of copper. Oh, that's right. So, copper with a molar mass of 63.5. Which comes out to 6.8, 6.35. Actual is 7.11. So I got closer than they did, but still a pretty rough estimate. All right. Concentration cells. A concentration cell is a type of galvanic cell. Like all galvanic cells, it contains two half cells connected by a conductive material, allows a spontaneous oxidation-reduction reaction to proceed, which generates a current and delivers energy. The distinguishing characteristic of a concentration cell is in its design. The electrodes are chemically identical. For example, if both electrodes are copper metal, they have the same reduction potential. Therefore, current is generated as a function of a concentration gradient established between the two solutions surrounding the electrodes. The concentration gradient results in a potential difference between the two compartments and drives the movement of electrons in the direction that results in equilibration of the ion gradient. The current will stop when the concentrations of ionic species in the half cells are equal. This implies that the voltage or electromotive force of a concentration cell is 0 when the concentrations are equal. The voltage as a function of concentrations can be calculated using the Nernst Equation. In a biological system, a concentration cell is best represented by the cell membrane of a neuron. As shown in figure 12.3, sodium and potassium cations and chlorine anions are exchanged as needed to produce an electrical potential. The actual value depends on both the concentration and charges of the ions. In this way, a resting membrane potential can be maintained. Disturbances of the resting membrane potential, if sufficiently large, may stimulate the firing of an action potential. And we have a diagram with salt on the left, which is outside the cell. And we have potassium on the right, which is inside the cell. And you see these concentration gradients of high concentration of sodium outside, high concentration of potassium inside, and also high concentration of chlorine outside. And we have a picture of a transporter protein transporting potassium across the membrane. All right. They don't give us equations, but they give us they tell us the Nernst equation. They just give us the name. Nernst. Type of galvanic cell. Think membrane potentials. In both neurons and other cells, muscle cells, a rechargeable cell or rechargeable battery is one that can function as both a galvanic and electrolytic cell. Let's write down rechargeable. Lead acid batteries. Lead acid. So nickel cadmium was an example of galvanic, I guess. Nickel cadmium. Is it CD? Where's that nickel cadmium at? Nickel cadmium is it's galvanic, I guess. I don't explicitly say that it's galvanic. I think it would be. It's not electrolytic. I don't think it's concentration. Lead acid batteries. A lead acid battery, also known as a lead storage battery, is a specific type of rechargeable battery. As a voltaic cell, when fully charged, it consists of two half cells, a lead anode, and a porous lead oxide cathode. Connected by a conductive material made of a concentrated 4 molar hydrogen sulfide, H2SO4 sulfate. H2SO4 is sulfuric acid. Concentrated sulfuric acid. When fully discharged, it consists of two lead sulfate electroplated lead electrodes with a dilute concentration of sulfuric acid. The oxidation half reaction at the lead negative anode is lead plus hydrogen sulfide sulfate, HSO4. It's hydrogen sulfate. Make lead sulfate and hydrogen ions. And the reduction half reaction at the lead positive cathode end is lead oxide plus sulfate ions plus hydrogen plus electrons makes lead sulfate and water. So let's draw this out so we can write these two reactions down. We got lead, got H2SO4 in the middle, got PbO2 on the right. And then in the second diagram, same chemicals. Oh no, now we got we don't have the same chemicals. Instead of the lead and the lead oxide, we have lead sulfate on both sides. And the sulfuric acid is diluted. And we're going to depict that by just making it smaller, less proportion of it. Why don't we exaggerate this even more? And we have the oxidation half reaction at the lead end. So this is the negative anode, this is the positive anode, cathode. Lead and the left side, you have Pb plus HSO4 minus makes PbSO4 plus H plus 2 electrons. And on the other side, we have PbO2 plus SO4 2 minus plus 4 H pluses plus 2 electrons makes PbSO4 plus 2H2O. Alright, give me a second. Alright. Both half reactions cause the electrodes to plate with lead sulfate and dilute the acid electrolyte when discharging. The lead anode is negatively charged and attracts the anionic bisulfate. The lead end is negatively charged and attracts the anionic bisulfate. So that's the hydrogen sulfate. All right, that's called bisulfate. The lead oxide cathode is a bit more complicated. This electrode is porous, which allows the electrolyte sulfuric acid to solvate the cathode into lead and oxide ions. Then the hydrogen ions in solution react with the oxide ions to produce water, and the remaining sulfate ions react with the lead to produce the electroplated lead sulfate. So those are the two reactions. Overall, the net equation for a discharging lead acid battery is lead plus lead oxide plus sulfuric acid make lead sulfate and water. These two together are lead plus lead oxide plus sulfuric acid make lead sulfate and water. When charging, the lead acid cell is part of an electrolytic circuit. These equations and electrode charge designations are the opposite because an external source reverses the electroplating process and concentrates the acid solution. This external source is very evident when one uses jumper cables to restart a car. Lead acid batteries, as compared to other cells, have some of the lowest energy to weight ratios, otherwise known as energy density. Energy density is a measure of a battery's ability to produce power as a function of its weight. Lead acid batteries therefore require a heavier amount of battery material to produce a certain output as compared to other batteries. So they have a low energy to weight ratio. Nickel-cadmium batteries are also rechargeable cells. They consist of two half cells made of solid cadmium, the anode, and nickel oxide hydroxide, the cathode, connected by conductive material, typically potassium hydroxide. Most of us are familiar with AA and AAA cells made of nickel-cadmium materials, inside of which the electrodes are layered and wrapped around in a cylinder, as shown in figure 12.5. So let's write down nickel, cadmium, so in the nickel-cadmium battery, the anode is cadmium, the cathode is nickel oxyhydroxide. Oxyhydroxide. What is oxyhydroxide? OH. So NiO and then another O, OH. And then the conductive material is KOH, potassium hydroxide. All right. Oxidation half reaction at the cadmium negative anode is CD plus 2OH minus make CdOH 2 plus 2 electrons. The reduction half reaction at the nickel oxide hydroxide positive cathode is 2 nickel oxyhydroxide. What is beeping over here? So 2 nickel oxyhydroxide plus 2 H2O plus 2 electrons makes 2 nickel dihydroxide plus 2 hydroxy ions. All right. Both half reactions cause the electrodes to plate with their respective products. Overall, the net equation for a nickel-cadmium battery is 2 NiOOH plus Cd plus 2 H2O make 2 NiOH2 plus CdOH2, and that's it. As in our previous example, charging reverses the electrolytic cell potentials. Some nickel-cadmium designs are invented for this reason to allow for the release of built-up hydrogen and oxygen gas during electrolysis. Nickel-cadmium batteries have a higher energy density than lead-acid batteries. The electrochemistry of the nickel-cadmium half reactions also tends to provide higher surge current. Surge currents are periods of large current early in the discharge cycle. This is preferable in appliances such as remote controls that demand rapid responses. It is important to note that modern nickel-cadmium batteries have largely been replaced by the more efficient nickel metal hydride batteries. These newer batteries have more energy density, are more cost-effective, and are significantly less toxic. As the name suggests, in lieu of a pure metal anode, a metal hydride is used instead. Surge currents, larger current in the beginning of the discharge cycle, and nickel metal hydride. Nickel metal hydride. Electrode charge designations. In a galvanic cell, current is spontaneously generated as electrons are released by the oxidized species at the anode and travel through the conductive material to the cathode, where reduction takes place. Because the anode of a galvanic cell is the source of electrons, it is considered the negative electrode. The cathode is considered the positive electrode, as shown in figure 12.1 previously. Electrons therefore move from negative, low electrical potential to positive, high electrical potential, while the current, the flow of positive charge, is from positive, high current electrical potential to negative, low. Conversely, the anode of an electrolytic cell is considered positive because it is attached to the positive pole of the external voltage source and attracts anions from the solution. The cathode of an electrolytic cell is considered negative because it is attached to the negative pole of the external voltage source and attracts cations from the solution. In spite of this difference in designating charge, oxidation always takes place at the anode and reduction always takes place at the cathode in both types of cells. Electrons always flow through the wire from anode to the cathode, and current flows from cathode to anode. Finally, note that regardless of its charge designation, the cathode always attracts cations and the anode always attracts anions. In the Daniell cell, for example, the electrons created by the anode at the anode by the oxidation of elemental zinc travel through the wire to the copper half cell. There they attract copper 2 cations to the cathode, resulting in the reduction of the copper ions to elemental copper and drawing cations out of the salt bridge into the compartment. The anode, having lost electrons, attracts anions from the salt bridge at the same time that zinc ions form by the oxidation process dissolve away from the anode. This is an important rule to understand not only for electrochemistry in the chemical and physical foundations section, but also for electrophoresis in both this section and biological and biochemical. Isoelectric focusing is a technique used to separate amino acids or polypeptides based on their isoelectric points. The positively charged amino acid protonated at the solution's pH will migrate toward the cathode. Negatively charged amino acids deprotonated by the solution will migrate toward the anode. The technique of isoelectric focusing is discussed in Chapter 3 of Biochemistry. All right. Circle which electrode each of the following statements describes in a galvanic cell. Site of oxidation, that would be the anode. Electron flow toward it. Electrons flow toward the anode. Current flows towards, current flows from the anode towards the cathode. Current flows to the anode from the cathode. Has a negative designation. The anode attracts cations. The cathode. Let me double check that I have that right. Galvanic cell, oxidation. Did they call it the anode? Yeah, they call it the anode. The electrolytic cell is where the plus is on the left, but minus on the left is anode. Circle which electrode each of the following statements describes in an electrolytic cell. In the electrolytic cell, the site of oxidation is still the cathode. Electron flow, or still the anode. Electron still flows towards the cathode. Current still flows towards the anode. The negative designation goes to the cathode and attracts cations, still the cathode. Write the cell diagram for the discharging state of a lead-acid battery. The cell diagram for a lead-acid battery. Well, I did it right here. Oh, they want me to write it with the bars and stuff. So anode solution, cathode solution. Anode, Pb and PbSO4, or no, HSO4. I guess it's the same solution for both of them, but it's sulfuric acid that's reacting on the cathode side, while it's the bisulfate reacting on the anode side. So I guess I'll write the bisulfate, PbHSO4. And then on the other side, Pb and PbO2 and SO4. I think that would do it. Oh, and they want concentrations, but I don't really know concentrations. Do I? No. Which type of cell has a positive delta G? A positive E cell. Positive delta G would be the electrolytic. Positive E cell. I think that's the galvanic, right? Double check real quick. If the EMF is negative, the cell must absorb energy. So positive is galvanic after all. All right. How much current is required to produce 0.23 kilograms sodium from a molten NaCl electrolytic cell that runs for 30 hours, assuming the cell is 100% efficient? So we want, what is this? This was 3, this is 5. 3 kilograms Na for 30 hours. How much current is required if you have 30 hours to do it? Well, 0.23 kilograms in salt. Let me double check what the equation is so we have the right stoichiometry. Where is that? Salt. Salt. They don't tell us, but it's just Na and Cl. So it's 1 electron per mole of, or per salt molecule. So we'll find our M equals IT over NF. And 0.23, 1, 2, 3, so 230 grams at Na is 23, Cl is 35, so that's 55.5. .230 divided by 55.5 equals 4.14 moles. Now we're going to put this into our equation. I is what we're looking for. T is 30 hours times 3600. So 108,000 over N is 1. It's 1 electron per molecule of salt. times 10 to the 5th. So you take this number, multiply it by 10 to the 5th. 2, 3, 4, 5. I'm going to divide it by 108,000. Current should be 3.84 volts. All right. Fill in the following chart to summarize electrode charge designations of batteries we have analyzed. Electrode charge designation. Galvanic or electrolytic. The nickel cadmium. While it's discharging, it's galvanic. While it's charging, it's electrolytic. When it's discharging, the anode is the cadmium, and the nickel oxyhydroxide is the cathode material. Charge on the anode is negative, charge on the cathode is positive. In this, while it's charging, it's the opposite. Molten sodium chloride. Discharging. So you put sodium while it's discharging, it's just while it's functioning. It's an electrolytic cell. Anode material is the chloride, and the charge is positive. Cathode material is sodium, and the charge is negative. For a Daniell cell, we have our, it's galvanic. You have zinc at the anode, and it's negative, and you have copper at the cathode, and it's positive. Lead acid, while it's charging, that would be it would be electrolytic. The anode material would be the lead oxide. The cathode material, and it's a positive, and it's a negative, and the cathode material is, it's still anode and cathode. It's just the sign changes, so it's negative on the cathode, it's positive on the anode. The anode is still the lead, cathode is still lead oxide. Let's see how we did on these. Why am I looking at discrete practice questions? I'm looking at answers to 12.1. In a galvanic cell, the anode is the site of oxidation, has current flowing toward it, and has a negative designation. The cathode has electrons flowing toward it and attracts cations. In an electrolytic cell, the anode is the site of oxidation and the current flowing towards it. The cathode has electrons flowing toward it, has a negative designation and attracts cations. Our equation looks similar to theirs, except we reversed the solution in the solvent. No. They have reversed the solution in the solvent. Maybe I have. So you put switch these two. H2SO4, PbO2, PbH2. Whoops. I guess that would be it. All right. Electrolytic cells are non-spontaneous and have a positive delta G. Galvanic cells are spontaneous and have a negative delta G. Therefore, they have a positive E cell. 5, they got 10, not around 8. What did we do wrong here? 230 grams, 23 grams per mole. So I did grams per mole for NaCl. They're just doing the Na. You don't count the weight of the Cl. So it's a little off. Should be times 1 mole over 23. So 230 divided by 23 is just 10. And then this will be 10 equals 1I times 108. Is that still right? Yeah, they didn't round like we did, but 1 mole. 30 hours times 3, 3,600 seconds. So let's do 10. Ten times 1, 2, 3, 4, 5 divided by 108. 1, 2, 3. So 9.25. So yeah, close to 10. They get 10. We got 9.25. The actual is 8.93. So it's a little closer, but 9.2526 volts. And it's not volts, it's amps. All right. And then the last one, nickel cadmium. When it's discharging, it's galvanic. When it's charging, it's electrolytic. The anode material is cadmium. The cathode material is nickel. Negative on the anode, positive on the cathode. What is this friggin' sound that's coming up? Who knows? All right. Nickel cadmium, when it's charging, it's electrolytic. And the cadmium hydroxide is the anode material, while the nickel is the cathode. I said it's still the same. Oh, wait. It is still the same anode and cathode. It's just the material is the hydroxide. dihydroxide instead of pure cadmium and nickel oxyhydroxide. We have molten salt. When it's discharging, it's electrolytic. Anode material, any material. Cathode material, any material, they said. The charge on the anode is positive, the charge on the cathode is negative. So I said it was salt and chlorine, but it's anything. The Daniell cell, when it's discharging, it's galvanic. You got zinc on the anode and copper on the cathode. Anode's negative, cathode is positive. Lead, when it's charging, it's electrolytic. You got the lead sulfate on the positive anode, and you got lead sulfate on the negative cathode. Is that what I said? I said, yeah, in both cases it's lead sulfate. But when it's discharging, it's galvanic, and the anode material is lead, cathode material is lead oxide. Anode is negative, cathode is positive. All right. I'm going to go to the bathroom real quick, and then we're going to get to 12.2, cell potentials. All right. Cell potentials. For galvanic cells, the direction of spontaneous movement of charge is from the anode, site of oxidation, to the cathode, site of reduction. This is simple enough to remember, but it begs the question, how do we determine which electrode species will be oxidized and which will be reduced? The relative tendencies of different chemical species to be reduced have been determined experimentally using the tendency of the hydrogen ion to be reduced as an arbitrary zero reference point. Reduction potentials. Reduction potential is movement in volts and is measured in volts and defined relative to the standard hydrogen electrode, SHE, which is given a potential of 0 volts by convention. The species in a reaction that will be oxidized or reduced can be determined from the reduction potential of each species, defined as the tendency of a species to gain electrons and to be reduced. Each species has its own intrinsic reduction potential. The more positive the potential, the greater the tendency to be reduced. Standard reduction potential, E not red for reduction, is measured under standard conditions 25 degrees Celsius, 1 atmosphere of pressure, and 1 molar concentration. The relative reactivities of different half cells can be compared to predict the direction of electron flow. A more positive E naught means a greater relative tendency for reduction to occur, while a less positive E naught means a greater relative tendency for oxidation to occur. For galvanic cells, the electrode with the more positive reduction potential is the cathode. The more positive reduction potential is the cathode, and the electrode with the less positive reduction potential is the anode. Because the species with a stronger tendency to gain electrons that wants to gain electrons more is actually doing so, the reaction is spontaneous and delta G is negative. For electrolytic cells, the electrode with the more positive reduction potential is forced by the external voltage to be oxidized and is therefore the anode. The electrode with the less positive reduction potential is forced to be reduced and is therefore the cathode. Because the movement of electrons is in the opposite different direction, in the direction against the tendency or desires of the respective electrochemical species, the reaction is non-spontaneous and delta G is positive. Given the following half reactions and delta naught values, determine which species would be oxidized and which would be reduced in a galvanic cell. Which species would be oxidized, which would be reduced? In a galvanic cell, the negative end will be oxidized, the positive will be reduced. They say that, yes, the silver will be reduced, and the, what is it, TL? What is TL? It's thallium. All right. It should be noted that reduction and oxidation are opposite processes. Therefore, to obtain the oxidation potential of a given half reaction, both the reduction half reaction and the sign of the reduction potential are reversed. For instance, for the example above, the oxidation half reaction and oxidation potential of the thallium are positive 0.34 volts. So the oxidation potential is in the opposite direction of the E naught. The reduction potential and the oxidation potential. The oxidation potential of thallium is the opposite of the reduction potential of thallium. That makes sense. Note that in the examples of batteries given above, lead acid storage batteries and nickel cadmium batteries, the oxidation half reaction was given with the reduction potential of the reverse reaction. These two quantities have equal magnitudes but opposite signs. On the MCAT, reduction potentials are generally given rather than oxidation potentials. Therefore, all references in this book, with exception to the thallium example immediately above, are given using reduction potentials, not oxidation potentials. All right. The electromotive force. Standard reduction potentials are also used to calculate the standard electromotive force, EMF, or E naught cell, of a reaction, which is the difference in potential voltage between two half cells under standard conditions. The EMF of a reaction is determined by calculating the difference in reduction potential between the two half cells. So this is electromotive force E naught of the cell equals E naught of the reduction or cathode minus the E naught of the reduction potential of the anode. By subtracting standard potentials, do not multiply them by the numbers of moles oxidized or reduced. This is because the potential of each electrode does not depend on the size of the electrode, the amount of material, but rather the identity of the material. The standard reduction potential of an electrode will not change unless the chemical identity of that electrode is changed. All right, given that the standard reduction potentials for SM3 plus and RHCl6 3 minus are negative 2.41 volts and plus 0.44 volts respectively, calculate the electromotive force of the following reaction. Do we really have to determine the half reactions? Can't we just add the numbers together? This is positive. This is going to be reduced. This is going to be... Oh, this is also reduced? No, this is a bunch of negative. So it's a negative charge. So this is a little bit positive. Example, SM3 plus RH plus 6Cl minus make RHCl6 3 minus the reduction potential for the SM is negative 2.41 volts. And for the RHCl6 is positive 0.44 volts. But this is not being reduced. This is being oxidized. So we'll put a negative, we'll reverse it. So we'll go yeah, RH on the anode. So the negative end, anode, is RH. This is going to be this one. The reduction potential of the cathode. Okay, you still use reduction potential, even though it's being oxidized. So 0.44 minus negative 2.41. .44 plus 2.41, 2.85. 2.85 volts. Great. they said if it were electrolytic, it would have been positive 2.85. But no, if it were a galvanic cell, it would be positive 2.85. But the cell is electrolytic. So we reversed it. It should be negative 2.41 minus 0.44. All right, whoops. Why is that? RH is oxidized, SM is reduced. Now we simply take the difference between the samarium reduction potential and the hexachlororodate reduction potential. We need not change the sign on the hexachlororodate because we are subtracting it from that of samarium. Cathode, anode. I guess we don't know that that's cathode and that's anode, do we? Point is, it's an electrolytic cell. So the point is, this is more positive. So the positive one is spontaneous. Here, the positive one is the RH. It will be reduced. RH is reduced. Is that what's happening here? 6 minus 6 for each of the chlorine. And it has a minus 3 total, so it's got to be plus 3 here. But they're saying this reaction is going to go that way. No, it's going to go this way. This will be oxidized, this will be reduced. Huh. So this will be reduced, and this will be oxidized. Reduced, oxidized. Anode, cathode. Oh, in a galvanic cell, but in an electrolytic cell, not the case. So how are you supposed to know that? I'm not really sure how you're supposed to know that it's which one is the cathode and which one is the anode. For galvanic cells, the electrode with the more positive reduction potential is the cathode. But looking at this, you can't tell whether it's which to use as the cathode or the anode. I guess it's that they gave us the SM and RHCl instead of just RH. You're supposed to be able to tell. You're supposed to know that. So first, determine the oxidation and reduction half reaction as written. Let's try that. So maybe that'll give us some, enlighten us. So from this, oh, it's the same problem. Two half reactions. SM3 is reduced plus electrons, plus 3 electrons, makes SM neutral. So that's reduction. And our H and chloride, so there's electrons on the right side, make RHCl6. 3 minus plus 3 electrons, and then these electrons cancel out when you add them together. So from this, SM is reduced, RH is oxidized. So because in the half reaction, SM is reduced, but from the voltages they give us, it looks like it should be oxidized. You're supposed to deduce that this reaction is happening in the opposite direction, and it is not a galvanic cell, but rather a electrolytic cell. I guess. All right. More examples. How are standard reduction potentials measured? How are standard reduction potentials measured? I guess by a multimeter. If a cell's electromotive force is denoted as a positive value, what does this mean? What is it? What if it is negative? If the electromotive force is positive, then it's a galvanic cell. If it's negative, it's electrolytic. Is that what they're talking about? Or that if it's positive, it's the anode or the cathode. It's if it's positive, it's spontaneous. If it's a negative, it's non-spontaneous. If it's positive, it's the cathode in a galvanic cell. Given the following reactions, determine whether the cell is galvanic or electrolytic. Good, more practice. 2Fe3 plus 2Cl makes 2Fe2 plus Cl2 in gaseous form. The rest is aqueous. Negative 0.59 volts. So it's got a negative EMF. So it's probably electrolytic, and the positive one is galvanic. Given the two half reactions below, what would be the spontaneous oxidation reduction reactions between these two species? This is positive. This is negative. This is greater, so the result will be positive. So delta G less than 0 is, oh no, but E over 0 is spontaneous. So it'll be spontaneous. Let's see what these answers are. The sample is measured by setting up a cell relative to a standard hydrogen electrode, which is given a reduction potential of 0. They're measured relative to 0. That's also true. A positive EMF means the cell is spontaneous. Negative EMF means it's non-spontaneous, right? First cell is electrolytic because it has a negative EMF. Second cell is galvanic because it has a positive EMF, right? 4, the reduction potential of triiodide is higher than iron 3, so triiodide will be reduced and iron will be oxidized. The positive will be reduced and the negative will be oxidized. Iron will be oxidized. Not whether it's spontaneous or not, necessarily. All right, electromotive force and thermodynamics. EMF and thermodynamics. Throughout our discussion of electrochemistry and the different types of electrochemical cells, we have been making references to the spontaneity or non-spontaneity of the redox reactions housed in each of the different cell types. Let's now look more formally at this topic by relating free energy to electromotive force and the concentrations of the oxidation reduction reactants and products to the voltage of a cell at a given point in time. Gibbs free energy. By now you should be familiar with the thermodynamic criterion for determining the spontaneity of a reaction, the change in Gibbs free energy, delta G. This is a change in the amount of energy available in a chemical system to do work. In an electrochemical cell, the work done is dependent on the number of coulombs of charge transferred and the energy available. Thus, delta G naught and EMF are related as follows. Delta G naught equals minus NF E naught of the cell, where delta G is the standard change in free energy, N is the number of moles of electrons exchanged, F is the Faraday constant, and E naught is the standard EMF of the cell. Gibbs free energy equals moles of electrons, Faraday's constant, EMF, Gibbs free energy. Faraday constant. Keep in mind that if the Faraday constant is expressed in coulombs, joules per volt, then delta G must be expressed in joules, not kilojoules. Notice the similarity of this relationship to that expressed in the physics formula, W equals Q delta V for the amount of work available or needed in the transport of a charge Q across a potential difference delta V equals N times F for the amount of work available or needed in the transport of a charge Q across a potential difference delta V, which is N times F is a charge. Notice the similarity of this relationship to that expressed in the physics formula. W equals Q delta V for the amount of work available or needed in the transport of a charge Q across a potential difference, delta V. N times F is a charge, and E naught is a voltage. This application in electrostatics is discussed in Chapter 5 of the physics. Note the significance of the negative sign on the right side of the equation. Delta G naught and E naught will always have opposite signs. Therefore, galvanic cells have negative delta G and positive E naught values. Electrolytic cells have positive delta G and negative E naught values. Let's note that if F in coulombs, then delta G in joules, not kilojoules. And delta G and E naught are always opposite sign. Determine the standard change in free energy of a cell with the following net reaction. Note the standard reduction potential of iron is 0.77 volts. The standard reduction potential of molecular chlorine is 1.36 volts. So, we have 2Fe3 plus 2Cl minus makes 2Fe2 plus Cl2 in gaseous form. I guess that's not too important. We have Fe3 plus 2 Fe3 plus 1 electron for each makes 2Fe2 plus. And then we have the other reaction, 2Cl minus makes chlorine and electrons. So this is reduction, this is oxidation. And they gave us numbers for them. Reduction, oxidation. Standard reduction potential of iron is 0.77. Of chlorine is 1.36. They're both positive. So, this is reduced, this is oxidized. If this is the reduction potential, are we going to actually see the opposite, 1.36 volts? This is greater. So I think the reverse reaction will happen. In this reaction, iron is reduced and is the cathode, where chlorine is oxidized and is the anode. The reduction potential of chlorine is actually higher than that of iron. This means that the electrodes are serving the opposite role from their natural tendency. And the reaction is non-spontaneous. This is an electrolytic cell and should have a negative EMF value. There you go. So then we'll take cathode and anode. Anode, cathode. No, cathode, reduced. Anode, oxidized. So, oxidized anode. And then we do plus, minus, minus. Cathode minus anode. So 0.77 minus negative 1.36. No, I guess we don't switch it to the oxidation number. We still use the reduction number. So it's just 0.7 minus 1.36. Which is 1.05 negative. Is 0.59, not 1.05. Volts. And then we use this delta G to find the delta G. Delta G equals moles of electrons minus two electrons per mole of product of reactant times Faraday's constant which we're just going to use 10 to the 5th. The EMF, negative 0.59. And that will equal $118,000. 1.14 times 10 to the 5th, or 1.2 times 10 to the 5th, or 1.18 times 10 to the 5th. positive. So 1, 2, 3, or 118 kilojoules. So it's non-spontaneous. Right. Great. All right. Reaction quotients. So far, we have considered the calculation of a cell's EMF only under standard conditions. However, electrochemical cells may have ionic concentrations that deviate from 1 molar. Also, for the concentration cell, the concentrations of the ions in the two compartments must be different for there to be a measurable voltage and current. Concentration and the EMF of the cell are related. EMF varies with the changing concentrations of the species in the cell. When conditions deviate from standard conditions, one can use the Nernst Equation. Nernst Equation. The electromotive force of the cell equals E naught of the cell minus RT over NF log Q, where E cell is the EMF of the cell under non-standard conditions, E naught is the EMF of the cell under standard conditions, R is the ideal gas constant, T is the temperature in Kelvin, N is the number of moles of electrons, and F is the Faraday constant, and Q is the reaction quotient for the reaction at a given point in time. The following simplified version of the equation can be used, assuming T equals 298 degrees Kelvin. And that is just 0.0592 over N times log Q. So that's just 298 times the ideal gas constant divided by Faraday's constant. So those are all the constants and temperature turned into one constant. Oh, and instead of a natural log, it's a log. I also took the E out of there. All right. This simplified version of the equation brings together RT and F and converts a natural logarithm to the base 10 logarithm to make calculations easier. Remember that the reaction quotient Q for a general reaction, AA plus BB plus little c big C plus little d big D, has the form Q equals C to the C, D to the D over A to the A, B to the B. All the expression for the reaction quotient Q has two terms for the concentration of reactants and two terms for the concentration of products. Remember that only the species in solution are included. When considering the case of Daniel's cell, for example, only the concentrations of zinc and copper ions are considered. So Q equals the concentration of zinc ions over the concentration of copper ions. The EMF of a cell can be measured with a voltmeter. A potentiometer is a kind of voltmeter that draws no current and gives a more accurate reading of the difference in potential between two electrodes. Concentration of zinc over concentration of copper. So I guess the anode is on top. Is that how it's always going to be? All right. Let's do an example. Find the EMF of a galvanic cell at 25 degrees Celsius based on the following standard reduction potentials. 25 degrees Celsius does happen to be 298 Kelvin, doesn't it? We have Fe2 plus 2 electrons makes Fe. We have chlorine plus 2 electrons makes chlorine ions, chloride ions. The reduction potential of the Fe reaction, of the iron reaction, is minus 0.44. The reduction potential of the chlorine reaction is plus 1.36. In this cell, Fe2 plus equals 0.01 m and chlorine ions equals 0.1 m. 0.1 molar and 0.01 molar for the iron. First, determine the standard cell potential. Because the chlorine half reaction has a higher reduction potential, it will be the cathode. Iron will act as the anode. Chlorine has a higher reduction potential, it'll act as the anode. So it'll be oxidized. Fe will be reduced. Anode, cathode. So 1.36 minus negative 0.44. 1.36 minus negative 0.44. Equals 1.8 volts. And then we use this. E naught of the cell, which is this. All right, so E cell equals 1.8 minus 0.0592 moles 2 electrons per log of Q. And Q in this case is is the anion. So it's the iron. 0.01 over 0.1. Log is -1. So that'll basically just, this whole thing basically just turns this into a positive. So it's basically just 1.8 plus 0.0592 over 2. 0.0592 divided by 2 plus 1.8 equals 1.83. They have 1.92 plus 2 times, did we do the same thing? Yeah, 0.0592 divided by 2, log of Q. They had said Q is these multiplied, not divided. So, since iron is being oxidized, the opposite is actually going to happen. It's going to be Fe to Fe2 plus 2 electrons. And the other half reaction, Cl2 plus 2 electrons, makes 2 Cl ions. So, since the ions are on the right either way, it's going to be the concentration of one times the concentration of the other. Because the net reaction is so here A, B, C, D, Q equals CD over AB. So in this case, C and D are the Fe and Cl concentrations. And there's no A and B. So, let's put this back into here. 0.1 times 0.01 equals 0.001. Log of 0.001 is -3. So this is still turned to a positive, but this is multiplied by 3. Because log of this equals 3. So instead of just 0.0592 divided by 2, 0.0592 divided by 2 times 3, and then plus 1.8. And then you get a number of 1.88. So we got the Q, put log of Q, log of 10 to the minus 4th. Because it's squared. Because there's 2 chlorine for every 1 Fe. So let's try it again. 0.1 squared times 0.01 is 0.0001. So it's 10 to the negative 4. And log of 10 to the negative 4 is 4. So let's turn this from a 3 into a 4. Squared. Which is 0.001. This is a 4. 0.0592 divided by 2 times 4 plus 1.8 is now 1.9. 0.92. In this case, the cell actually has a higher voltage than it normally would due to the concentrations of ions present. Great. All right. Equilibria. As discussed in Chapter 7, delta G naught can also be determined in another manner. Delta G naught equals minus RT log, natural log, of KEQ. Where R is the ideal gas constant, T is the absolute temperature, and KEQ is the equilibrium constant for the reaction. Combining the two expressions that solve for standard free energy change, we see that delta G naught equals minus NF E naught, which equals minus RT log KEQ, or NF E naught equals RT natural log KEQ. So NF E naught of the cell equals RT natural log of KEQ. By extension, if the values for NT and KEQ are known, the E naught for the reaction is easily calculated. On the MCAT, you will not be expected to calculate natural logarithm values in your head. That being said, these equations can still be tested, but in a conceptual way. Analysis of the equations shows us that for redox reactions with equilibrium constants less than 1, equilibrium state favors the reactants. The E naught of the cell will be negative because the natural logarithm of any number between 0 and 1 is negative. These properties are characteristic of electrolytic cells, which house non-spontaneous oxidation-reduction reactions. Instead, if the equilibrium constant for the reaction is greater than 1, the equilibrium state favors the products. The E naught of the cell will be positive because the natural logarithm of any number greater than 1 is positive. These properties are characteristic of galvanic cells, which house spontaneous oxidation reduction reactions. If the equilibrium constant is equal to 1, concentrations of the reactants and products are equal at equilibrium. The E naught of the cell will be equal to 0. An easy way to remember this is that E naught cell equals 0 for any concentration cell with equal molar concentrations on both half cells because there is no net ionic equation. Both half cells contain the same ions. Knowing the effects of concentration on equilibria, we can now derive the change in Gibbs free energy of an electrochemical cell with varying concentrations using the equation. Delta G equals delta G naught plus RT log Q, where delta G is the free energy change under non-standard conditions. Delta G naught is the free energy change under standard conditions, which can be determined from equation 12.4 or 12.8. R is the ideal gas constant, T is the temperature, and Q is the reaction quotient. Delta G equals delta G naught plus RT natural log of Q. Before you move on, assess your understanding of the material with these questions. Fill in the table to show the relationships between the equilibrium constant, Gibbs free energy, and electromotive force, assuming standard conditions. At a KEQ of 1.2 times 10 to the minus 2, less than 1, delta G will be positive, reaction will be non-spontaneous, and the electromotive force of the cell will be negative. At a higher than 1, delta G will be negative, it will be spontaneous, and the electromotive force of the cell will be positive. At 1, delta G will be 0, it will be in equilibrium, and E naught of the cell will also be 0. Given the following reaction quotients and equilibrium constants, determine the direction of the reaction and the sign of E cell. At a Q of 10 to the minus 3, log of Q is 3, or minus 3. Oh, Q, KEQ. All right, so we're relating KEQ, Q, and sign of E cell. So when KEQ is less than 1, the sign of E of the cell is also minus, is negative. Reaction direction is backward. If Q, delta G is going to be your G naught plus RT log Q. So, if KEQ is less than 1, this will be negative. It turns to a positive. Delta G will be positive. So positive plus Q is also going to be negative. Log of KEQ is going to be, negative. So positive plus a negative. It looks like it's a KEQ is 2, so it's going to be like a 2 plus negative 3. Yeah, so if delta G is negative, then it proceeds in the forward direction. Because I guess Q is greater than KEQ, so proceeds in the forward direction. Sign of E is positive. Let's see. I mean, we can assume it's positive. We know E naught, but we don't know the E of the cell, the instantaneous E of the cell. So, yeah, we'll assume it's positive. Next one is going to be something smaller than 1 and 1. So, similarly, we'll put this number. What's a log of 1? Is 0. So it's basically 0 plus minus 2. Also forward direction, and sign of E cell is positive. Last one, 1. So it's 0 plus 0 in equilibrium. Sign of E cell is also 0. Let's see how we did on those. 12.3. The first one, 1.2 times 10 to the minus 2. What did I say? I don't remember what I said now even. I said KEQ of less than 1 means delta G is positive, non-spontaneous, E cell is negative. Positive, non-spontaneous, negative. The next one, greater than 1, negative, spontaneous, positive. At 1, delta G is 0. It's at equilibrium, and E naught is also 0. Now for the second problem, remembering that delta G naught equals minus RT log KEQ. If KEQ is less than 1, log KEQ is less than 0, and delta G is greater than 0. If KEQ is greater than 1, log KEQ is greater than 0, and delta G is less than 0. If KEQ equals 1, log of KEQ equals 0, and delta G equals 0. So the first one was forward, but the second one was backwards. And the third one is equilibrium, but why is the second one backwards? KEQ greater than 1, log KEQ greater than 0, delta G less than 0. Oh, you know what? It's not 10 to the minus 2. It's 10 to the 2. Oh, this says minus 2. While this says 10 to the 2. If it were, in fact, 10 to the 2, this was not a minus, this was a plus, then indeed it would be the backward reaction that they're expecting. I think that's got to be a typo. They said 10 to the minus 2 here, but they meant 10 to the 2. Because if you change the sign on this over here, it becomes 0 plus 2 instead of 0 minus 2. And then you get a positive 2 instead of a negative 2 is what they're going for. So yet another typo on the fantastic Kaplan study guides. I highly recommend the Kaplan study guides if you like lots of typos. All right. Practice questions. In 1 second. I'll take another bathroom break real quick. Finish this up. All right. Now for some practice questions. All right. Rusting, number 1. Rusting occurs due to the oxidation-reduction reaction of iron with environmental oxygen. 4Fe in solid form plus 3O2 in gaseous form make 2Fe2O3 in solid form. Some metals cannot react with oxygen in this fashion. Which of the following best explains why iron can? Iron has a more positive reduction potential than those metals, making it more likely to donate electrons to oxygen. Iron has a more positive reduction potential than those metals, making it more likely to accept electrons from oxygen. Iron has a less positive reduction potential, making it more likely to donate, or has a less positive reduction potential, making it more likely to accept. Well, reduction potential makes it more likely to gain an electron. Reduction is gain. So having a higher reduction potential means it reduces the opposite, the other one. Oh, I don't remember now. I gotta look back. Higher reduction potential makes it the anode, makes it the, or no, higher reduction potential makes it the cathode. And the cathode is reduced. More likely to accept electron. More positive reduction potential and more likely to accept electron. 1B. I guess we don't really need this equation. We're just going to go with B. 2. Given the following standard reduction potentials, zinc plus 2 electrons makes zinc. Silver ions plus electrons make silver. What is the standard electromotive force of the following reaction? So the reduction potential is more positive on the silver, meaning silver will be the cathode, which means silver will be reduced. So plus electrons is reduction. This is correct in the forward. This will happen in the reverse. Or no, not necessarily. Yeah, this will happen in the reverse. The electrons got to go up here. Silver and zinc. So silver will be 0.337 minus the opposite of this. So minus 0.763, I think. But they have it in the opposite. What is the standard electromotive force of the following reaction? So it'll be the opposite of this, I guess. 0.337 minus 0.763 is 0.426. So maybe I have to do stoichiometry. I get 2 electrons for every one of these. I have to multiply it by 2. Or did I just do this wrong? 0.337 plus 0.763 equals 1.1. This is positive. This should be the cathode. This should be the anode. Anode to cathode. Okay, that looks right. So it's the reverse of this. It's minus 0.337. No, you don't reverse it. You keep the same. Yeah, you don't reverse anything. Why am I reversing stuff? It's minus negative. this is going to accept electrons. It's going to be the cathode. So this thing is going to be formed. And this thing is going to be formed. So it's in the right direction. So it's positive 1.1 volts. But do I need 2? Do I get 2 electrons for every... So I use 2 zinc, 2 electrons. I don't think you have to do stoichiometry. I'm just going to go with 1.1. C. 3. Consider the following data. Mercury ions plus 2 electrons makes elemental mercury with a reduction potential of 0.85. Copper ions to copper, 0.52. Zinc ions to zinc, negative 0.76. Aluminum ions to aluminum, negative 1.6. The anode of a certain galvanic cell is composed of copper. Which of the metals from the data table can be used as the cathode, assuming equal concentrations of the 2 electrolyte solutions? So the anode is copper, is Cu. And the anode should be negative, the cathode should be positive. So I just need something more positive than 0.52. 0.85, 0.7, 0.8, 1.6 is negative, So the only one more positive is the mercury, 1A. An electrolytic cell is filled with water. Number 4. Which of the following will move toward the cathode of such a cell? So moving towards the cathode of an electrolytic cell. So I think for the electrolytic cell, the cathode and anode are reversed. Just the sign on the cathode and anode are reversed. But this is what we're looking at. Electrons going to the negative cathode. Positive anode. But on a battery, it'll be positive, negative. Is there something I can do with this? Can I copy this? It'd be great if there was a shortcut to copy this, huh? Alright, anyways. Did it actually travel with me for a little bit? Oh, look at that. You can. H plus ions. So they're talking about in the container. Hydrogen ions. So let me double check. Positive ions go towards the negative end. So hydrogen will go towards the negative end, the cathode, towards the cathode. Positive, these will go, but also electrons through the wire will go towards the cathode. So H in electrons, 1 and 3. 1 and 3 only. 4 is C. I like this. I'm going to keep this here. This doesn't say what's on each side. Positive Na plus Cl minus. All right, number 5. If the value of E naught is known, what other data is needed to calculate delta G? If E naught of the cell is known, to calculate delta G naught, all you need is the reaction quotient, N. Half reactions, temperature of the system, equilibrium constant, reaction quotient, because this equals delta G minus delta G. We had another equation for that, right? Minus delta G. All right. Reaction quotient, B. 6. Which of the following compounds is least likely to be found in the salt bridge of a galvanic cell? What do we remember about salt bridges? KCl, NH4NO3. They have to be things that don't themselves react, I guess. NH4NO3 is a good one. KCl, so maybe NaCl is good. MgSO3, that's good. Just SO3 probably isn't good, right? Because you have to have positive and negative ions. Each of these has positive and negative ions, but this just has, it's just a negative, right? So not B. If the surface area, number 7, if the surface area of electrode material in an electrochemical cell is tripled, what else is necessarily tripled? Current, KEQ, E naught of the cell. They say 1 only, 2 only, 1 and 2 only, 2 and 3 only. Is the electromotive force tripled? Is the current tripled? Is the KEQ tripled? What's dependent on moles and what isn't? Electromotive force isn't dependent on moles, right? Right, what they were talking about here, they said that, this would be that little part again. Energy density cell potential. When subtracting standard potentials, do not multiply them by the number of moles, oxidized or reduced. This is because the potential of each electrode does not depend on the size of the electrode, the amount of material, but rather the identity of the material. The standard reduction potential of an electrode will not change unless the chemical identity of that electrode is changed. So it's not EMF. Seven. It's not the E naught. So it's not current either. It's just KEQ, right? One only, two only, one and two only, two and three only, two and three only. If the EMF of the cell doesn't change, would the current change? The E cell doesn't change. Where's the term with current in it? This one. Moles equals current times time over moles times F. So current is related to how much material. So yes. What else is necessarily tripled? Current is tripled. KEQ will also be tripled, right? Or maybe not the equilibrium constant. Yeah, KEQ. Oh, is it 2 only? Remind me what the equilibrium constant is. I guess KEQ doesn't change, does it? KEQ versus Q. Q is a numerical value at the end of the reaction, but it still depends on equilibrium constant versus reaction quotient. Equilibrium constant. Equilibrium constants are not changed if you change the concentration of things present in the equilibrium. All right, so the only thing that changes is current. 7 is B. Number 8. Which of the following can alter the EMF of an electrochemical cell? The mass of the electrodes, the length of the wire connecting the half cells, the overall size of the battery, the temperature of the solutions in the half cells. Now, of all of these, the temperature sounds most promising. Let's go with temperature. Nine, which of the following statements could be true about a NaCd cell, sodium cadmium cell, based on the information below? They both have negative EMFs. This one is the more positive one, the 0.4 cadmium. Sodium is 2.7, negative 2.7. Cadmium is negative 0.4. Cadmium is the more positive. So cadmium will be the cathode. Sodium is the anode. So anode is losing electrons. Anode is losing electrons. No. Yeah. The anode is going from Na to Na+. The cathode is going from Cd2+ to Cd. It's being reduced. Cathode is reduced. Anode is oxidized. So the E naught of the cell equals the E naught of the cathode minus the anode. So negative 0.4 minus negative 2.71, which equals what, 2.71 minus 4, 2.31. So EMF is positive. So it is a galvanic cell. But I don't get the same number as them here. Did I mess up trying to do this before too? This one's more positive. This is the cathode. Is it an electrolytic cell? And when I take the cathode minus the anode, I get a positive number. So I guess I'll go 3.11 volts. It's got to be a galvanic cell. What if it was minus 2.71 minus negative 0.4? Yeah, no difference. Still 2.3 instead of 3.1. Whoops. Let's see. 2.71 plus 0.4 is 3.1. So maybe it's negative 0.4 minus 2.7. It is minus, right? Anode, cathode. I have to reverse one of these. We decided that it was happening in the forward direction, meaning the cathode is on the right. Cathode is... No, the anode is reversed. I guess we should write some half reactions, huh? Let's try doing that. Or combining these into a reaction. So CD on the cathode side, ions are becoming solid. You're losing ions. They're being reduced. So the cathode side is being reduced. The anode side is being oxidized. So the reverse is happening. So negative 0.4 minus positive 2.71 equals minus 3.11. So, but that makes it an electrolytic cell. Now we're going to go with galvanic cell in 3.11 volts. That's what we're going to do. Or maybe it's an electrolytic cell. More positive is the cathode. Cathode minus anode is the E cell. Electrolytic cell in cadmium is the anode. That's not true. So yeah, it's got to be this last one then. What if I reverse this one? What if I made it 0.4 minus negative 2.71? 3.11. What I did is reverse this one. Oops. So this is being reduced, this is being oxidized. I want it the other way. I do want CD 2 plus Na makes Na plus CD. So now this is being reduced, this is being oxidized. What was done is that this reaction was reversed. So this number has to be reversed, turn positive. It's got to be negative 3.11. Yes. Final answer, 9 is D. 10. Which of the following expressions correctly describes the relationship between standard electromotive force and standard change in free energy? Electromotive force in Gibbs free energy? We decided this equals negative NFE cell. So delta G naught equals negative NF, and then the E to the cell is replaced by E naught anode minus E naught cathode. Now it's supposed to be E naught cathode minus E naught anode, so that's not right. We have E to the E naught of the cell equals NF over RT log KEQ. So it's just not right. Because it should be R to the T over NF log KEQ. But that's not quite right. So this is actually right. Even though they forgot the minus, they switched anode and cathode, so that does the same as reversing the minus, right? Right? Does that make sense? Minus 12. Yeah. So D looks the most right to me. Let's go with D. C is wrong because it's not KEQ, it's supposed to be Q. KEQ doesn't change. Q changes. It's supposed to be... So that's wrong, as well as this is E naught of the cell. Oh no, that makes sense. E naught of the cell equals minus RT NF over NF log of KEQ. Is that right? No, I like D. D is better. 11. Which of the following choices is indicative of a spontaneous reaction assuming standard conditions? E naught of the cell is negative. No. Q equals KEQ. No, then you're in equilibrium. The cell is a concentration cell. Well, it depends on where concentrations are. If KEQ is greater than 1, then it is spontaneous and in forward. 12. For a cell with the following half reactions, how would decreasing the pH of the solution inside the cell affect the electromotive force? So we have cathode, PD, palladium, ions plus electrons makes elemental palladium. They're saying that's the cathode. Yeah. The anode is making electrons. And it's on the right side of the equation, so we don't have to reverse it or anything. How would decreasing the pH of the solution inside the cell affect the electromotive force? Well, if you decrease the pH, you're adding protons. So it's going to shift to the left. It's going to go in the opposite direction. So the EMF would decrease. Remain the same, increase, become 0, it would decrease. I think it would decrease. An electrolytic cell necessarily has a delta S greater than 0, delta G less than 0. That's not true. KEQ less than 1. Yeah, that sounds right. An E cell greater than 0. S entropy, I don't know. We didn't talk about this chapter, so we're going to skip that. E naught of the cell greater than 0 is for a galvanic cell. Delta G less than 0 is for a galvanic cell. KEQ less than 1 would be electrolytic, right? 13C. I mean, so that would be like a what do you call it? A concentration cell acting as an electrolytic cell. No. Oh yeah, it has a KEQ less than 1 just because it doesn't want to go forward in the forward direction. It prefers reactants. 14. Which of the following is the best explanation for the fact that a larger mass of electrodes are required for lead-acid batteries as compared to other batteries to produce a certain current? The lead-acid electrolyte, sulfuric acid, is diprotic and incompletely dissociates in solution. B, the energy density of lead-acid electrodes is higher than that of other batteries. The electrolytes in other batteries less readily dissociate than those of lead-acid batteries. The energy density of lead-acid electrodes is lower than that of other batteries. So the energy density is lower. That's true, right? We said that. But is that the best explanation for the fact that a larger mass of electrodes are required? No, yeah, I think it's just the energy density. Let's go with the energy density. 14D. What did I do with 13? 13 was C. And I said 3. C. Which of the following best describes why overcharging a nickel-cadmium battery is not detrimental? A, the energy density of a nickel-cadmium battery is high, so it can store more charge than other batteries per its mass. B, the electrodes of a nickel-cadmium battery can discharge through the circuit when they are fully charged. C, the nickel-cadmium battery will stop accepting electrons from an outside source when the electrodes are charged. D, nickel-cadmium batteries have a high surge current and can dissipate the overcharge before damage can occur to electrodes. They do have a high surge current. I don't know if that means that they can dissipate overcharge. Nickel-cadmium battery will stop accepting electrons from an outside source when its electrodes are recharged. That's what it seems like. I mean, that's what phones seem to act like, but I don't know if that's because, they have internal circuits making that happen. You're pushing electrons against the gradient when you're charging. So once you've pushed all the electrons you can push, what happens to that extra current. B, the electrodes of a nickel-cadmium battery can discharge through the circuit when they are fully charged. That makes sense, because like, yeah, the same thing is used to recharge as a electrolytic and as a galvanic cell. So you're pushing electricity into it, but when you stop doing that, it'll just push it back. So I mean, the energy density of a nickel-cadmium battery is high, so it can store more charge than other batteries per its mass. It does have a high energy density, but I don't know why that makes it like why it would not be detrimental, less detrimental to overcharge. OBS reconnection successful. Sure hope so. All right. 1 is C, not B. In the oxidation-reduction reaction of metal with oxygen, the metal will be oxidized, donating electrons, and oxygen will be reduced, accepting electrons. This fact allows us to immediately eliminate choices B and D. A species with a higher reduction potential is more likely to be reduced, and a species with a lower reduction potential is more likely to be oxidized. Based on the information in the question, iron is oxidized more readily than those metals. This means that iron has a lower reduction potential. You know, I just assumed that Fe plus was going to Fe, but if you look at this reaction and actually put all the oxidation states in there, I guess that's not the case, huh? When you do oxidation states, you start with oxygen minus 2 times 3 is minus 6, divided by 2 is 3. So here's the 3 plus over here. And then on the left side, you have 4Fe solid, so that's neutral, plus 3O2 in gaseous form, so it's also neutral. So you have oxygen going from 0 to negative 2, and iron going from 0 to positive 3. So iron is being oxidized, oxygen is being reduced. So iron is losing electrons. So donate electrons. So A or C. So donating electrons, the positive one is reduced. The more negative one, so the less positive reduction potential is reduced, is oxidized. So right, It is C. I didn't actually go through and look at the oxidation states. I guess I just assumed Fe plus, but no, it's neutral Fe to Fe plus. Iron is reduced. No, oxidized. Iron is oxidized. All right. So that's 1. 2 is B, not C. Let's see what we did here. To determine the standard electromotive force of a cell, simply subtract the standard reduction potentials of the two electrodes. In this case, the cathode is zinc because it is being reduced. The anode is silver because it is being oxidized. Thus, negative 0.763 minus 0.33 equals negative 1.1 volts. You must multiply the silver half reaction by 2 to balance electrons. The actual value of the reduction potential does not change. Remember that the standard reduction potential is determined by the identity of the electrode, not the amount of it present. So, 2, what did I do? I said it was positive 1.1. They said negative. So I went with the positive. Ag will be the cathode. No? Is that what they said? Cathode is zinc because it is being reduced. The anode is silver because it's being oxidized. I thought the more positive one is the cathode. But they gave us a reaction in which zinc is being reduced and silver is being oxidized. So regardless of the electromotive force, they give us this reaction. So this is what they want us to do. So we should have just gone with cathode 0.337 zinc is being reduced, this is being oxidized. Reduced is cathode. Cathode is negative 0.7 minus the anode 0.337 equals negative 1.1. B. All right. They gave us this equation. So regardless of what these are doing, that's the reaction we're talking about, not the reverse. You see, it has a negative voltage, which means it takes power to do it, right? All right. 3 is going to be A, 4 is going to be C, 5 is going to be D, not B. The answer comes directly from the equation relating Gibbs free energy and E naught of the cell. Delta G naught equals negative NF E naught of the cell, where N is the number of moles of electrons transferred and F is the Faraday constant. To determine N, one must look at the balanced half reactions occurring in the oxidation-reduction reaction. So 5D half reactions of the cells. I said reaction quotient. Okay, so I confused reaction quotient is Q, huh? I was thinking moles, N. So to get N, you use the half reactions to see, 2 electrons on one side, 1 on the other. So there's a 2-to-1 ratio. So it's half reactions. 5 is D. 6 is B. 7 is also B. 8 is D. 9 is B, not D. If this were a galvanic cell, the species with a more positive reduction potential, cadmium, would be reduced. The cathode is always reduced in an electrochemical cell, so sodium could not be the cathode in such a galvanic cell. Eliminating choice A. Sodium would be the cathode in an electrolytic cell, however, which would make cadmium the anode. Thus, the answer is choice B. Note that we do not have to determine E cell because we already know the answer. However, the E cell would be negative 2.7 minus negative 0.4, which is negative 2.31 volts for an electrolytic cell, and positive 2.31 volts for a galvanic cell, eliminating choice C and D. So the first cathode is reduced. Sodium could not be reduced. 9. No, we said that this is being reduced. So we correctly eliminated sodium is the cathode. It is an electrolytic cell and cadmium is the anode. So sodium is the cathode if it were a galvanic cell. I said it's an electrolytic cell, the negative 3.11 volts. But that is not right. You don't have to switch around the numbers like that. It is at 2.31, they said. They said it is an electrolytic cell. In an electrolytic cell, cathode, anode, So once again, I started with that premise that this is more positive. This should be the cathode. If it were a galvanic cell, the species with a more positive reduction potential, cadmium, would be reduced. Right. The cathode is always reduced in an electrochemical cell, so sodium could not be the cathode in such a galvanic cell. So yes, sodium could not be the cathode. The cathode is always reduced, eliminating choice A. Sodium would be the cathode in an electrolytic cell, however, which would make cadmium the anode. Oh, right. So that's for a galvanic cell. All right. Right. Well, if it was a galvanic cell, sodium could not be the cathode. If it's an electrolytic cell, cadmium can be the anode. And if it's an electrolytic cell, E naught cannot be negative 3.1. It would still be negative 2.3. Cadmium is the anode. Sodium is the cathode. It would be negative 2.71 minus negative 0.4. Negative 2.31. So it can't be D. Cadmium is the anode because it is electrolytic. 9B. 10 is D. 11 is D. 12 is A. 13 is C. 14 is D. And 15 is C, not B. During the recharge cycle, nickel-cadmium cells will accept current from an outside source until the cadmium and nickel oxyhydroxide electrodes are pure. At this point, the reaction will stop because cadmium oxide runs out and no more electrons can be accepted. A and B are true statements, but they fail to explain why overcharging the battery is not a problem. Finally, surge current refers to initial burst of current seen in some batteries. Once charged, the surge current will not increase even if the power source continues to be run because no additional charge will be stored in the electrodes, eliminating choice D. These two are true, but don't explain why overcharging is not detrimental. C, they'll just stop accepting electrons because all of the reactants have been converted. Well, there you have it. That is electrochemistry. And that is MCAT general chemistry. Next time we'll have to get into either organic or biochemistry. Probably organic. We'll continue with the chemistry because organic chemistry will be useful in biochemistry.